All right, we'll go ahead and get started. So it's my pleasure today to introduce Professor Teague, visiting us from MIT. He got his PhD at Max Planck Institute, after which he went on as a postdoc at University of Michigan, followed by being a submillimeter array fellow at CFA before starting as a professor 2 years ago now at MIT. He's an expert in observational planet formation, I guess. He's going to tell us today about from pebbles to planets. So, take it away.
Thank you very much. It's really wonderful to be here and share with you some of our recent results. I think the field of planet formation is one that is moving on at a tremendous rate thanks to the new facilities that we have to observe the planet forming disks out there. We're learning a tremendous amount, and I think we're really transforming the science from a very quantitative picture of how planets formed to a qualitative one where we can really compare to our models, our numerical simulations, and really understand how planets are forming. Now, I think that planet formation is a particularly special sort of part of astronomy because it's one of the few fields where we can go beyond remote sensing. We can actually visit examples of the objects that we're studying. So within our own solar system, we can send these probes out to the gas giants and we can graze their atmospheres to understand what's in there. We can land small satellites on sort of these rubble piles, these meteorites, asteroids, grab samples from them and return them back to our labs here on Earth so we can analyze them in great detail to really understand the composition of these bodies. And so this means that we're in a really privileged position in that we know the distribution of materials and objects in our solar system to really an exquisite level of detail. And this is really great when we want to try and recreate the formation history of our own solar system because we have a lot of things that we need to match and a lot of observables to reproduce. The problem is we're starting to see that the solar system perhaps isn't as common as we'd expect. When we start to look for exoplanets or planets beyond our own solar system, so exoplanets, we're seeing that there's a huge diversity in really fundamental properties of these systems. And that's what I'm trying to convey with these two figures here. These are the distributions of the masses of the planets that we've detected outside our solar system in blue, and their orbital radii in red. And so underneath each of these, I've plotted where our 8 planets in our solar system lie. And so when we look at the mass of the planets, you can see that there's a pretty good spread over most of the planets in our system. We're not really seeing anything down at the Mercury and Venus regime, and that's perhaps expected. These are too small to really be detected. But we're seeing these 2 large peaks up here, one between sort of Earth mass planets and Neptune mass planets, so super Earths or sub-Neptunes, and also this very large peak here, very massive planets, so things that are much more massive. Much more massive than Jupiter, and sort of really butting up against what we would consider to be a star. Similarly, when we look at the separation of these planets from their host stars, we can see a huge range that's covered by our solar system, but we're seeing another population of planets that are sitting really close in next to their host stars. These are these hot Jupiters. So when we want to think about a planet formation process, not only do we have to reproduce the wonderful data that we have of our own solar system, where we know things to this exquisite level of precision, but we've also got to use those same formation models to explain this diversity that we're seeing outside our solar system. And that's really the challenge, that you can do both of them with minimal fine-tuning. So really what we want to try and do is develop a recipe for making planetary systems, something that we can sort of simulate in our computers and then compare the outcomes to the populations that we're seeing. And there's sort of 3 things that we want for this recipe. We want to look at the ingredients, the methods, and the outcomes. So in terms of the ingredients, we want to know how much material is out there for making planets. What's the composition of that material and how is that distributed around the young star? In terms of methods, we want to know how we're then going to combine those materials to form the planets that we're seeing. If we're going to stretch this baking analogy a little bit further, you can imagine that you wouldn't want to use a blender to make scrambled eggs, and the exact same thing happens with planets. We have a disk that's highly turbulent and everything's getting mixed up. We're never going to be able to make those big Jupiter mass planets if everything is just disrupted at much smaller scales. Finally, we want to have a look at what the outcome of this process is. What are the planets that we're actually making? So I've said that we've detected a huge number of planets outside our solar system, but these are really old examples of planets, and planets will undergo a lot of evolution once they formed during their lifetime. What we want to understand is, what do the planets look like just after they formed, so in the first million years of their life, because that's really what we want to compare to. And so these are the three components that I'm going to step through in my talk today and try and describe to you how we've made significant progress in each three of these categories. So as I said, planet formation has really come on in leaps and bounds, particularly in the last decade, thanks to this particular telescope. This is ALMA, the Atacama Large Millimeter Array, and this is a sub-millimeter interferometer up in the Atacama Desert in Chile. It consists of these sort of 55 dishes. Each of these are 12 meters in diameter. So these are really huge things that you don't really appreciate on a pitch like this. And they're distributed across the plains up there with baselines of up to 16 kilometers. So you can really synthesize a radio telescope with a diameter of 16 kilometers. And this sort of telescope is why we're able to make such progress in planet formation, because it's allowing us to spatially resolve the distribution of material within these systems. So we've also been particularly lucky as a community in terms of the planet formation community and able to get time on this telescope. So observing time is always competitive, but I feel as a community we've done exceptionally well at getting the time we need to make the progress that we want to. And a lot of this comes down to getting what are so-called large programs here. So these are big programs devoted to sort of extended observations, where you bring together a large collection of the community to work on a single topic. And we've had 6 of them so far, focused on planet formation on ALMA. So we have D-Sharp, which was really looking at the dust distribution in the disks. We have MAPS, which is looking at the chemical complexity of these disks. H-Pro, looking at the evolution of gas throughout the lifetime of a protoplanetary disk. ExoAlma, which is the one I'm leading, looking at the dynamical structure of the disk. ARCS, looking at debris disks, so the phase after planet formation occurs. And DECO, which is a large sample of chemistry. So looking at chemistry on a much larger sample than we have before. And so all these large programs are really greater than the sum of their parts, in the sense that it gives us the data and sort of the manpower to make sense of that data to really make the leaps that we can't do with smaller sort of individual programs. And so a lot of what I'm going to show you today is work that's come out of this ExoAlma program, which is a large program that I've been leading, along with these 5 people, so Miriam Benesti, Stefano Puccini, Christoph Bunt, and Minato Fukugawa. We've been leading this for the last 2 years or so, with this group of people trying to make sense of the data. There's a whole number of graduate students in there that I've tried to highlight in bold. And this has really been a fantastic community of people. We've learned a lot about the data. We've learned a lot about the issues of observing with ALMA. We've also made, I think, tremendous progress in understanding that data, and particularly developing and refining our models of planet formation. So I want to begin by thinking about the ingredients. How much material is there to make planets, and what's the chemical composition of it? So when ALMA came online, we were very quick as a community to start trying to map out how much dust and how much gas are in these systems. And we started obtaining data that look like this. So these are snapshots, very, very short integrations of a whole variety of very nearby protoplanetary disks to try and understand how much gas is there and how much dust. And if we make a couple of assumptions that are fairly basic, but I think defensible, we can convert the integrated fluxes that we measure into a total mass of the disk. So we make assumptions about the optical depth of the system, the temperature, but we can use these very short snapshot images to gain some handle on how much material is in these disks. And so this is a compilation of all the gas masses for one particular star-forming region, Lupus. And you can see that there's a variety of values that we get here, but they're around 10 to the minus 3 solar masses, so around a Jupiter mass of gas. And this is pretty low, so this doesn't seem like, if there's only a Jupiter's worth of gas there, how are we going to make planetary systems that perhaps have more than one Jupiter in there? Nonetheless, this was sort of a starting point. We had these snapshot surveys and we had an idea of order of magnitude how much material was there.
Question?
Yeah.
What age are these systems?
So these systems, so this one's a couple of million years old. So we only have rough error bars on them, but most of what we're going to talk about now are things that are sort of 2 to 3 million years. So things started to change fairly rapidly when we sort of really exploited those long baselines that ALMA could provide us. So we went from being able to just map the total integrated flux coming out from the dust, where you had images that look like this, big and blurry, to ones where you can really map out the distribution of where those grains are sitting in the protoplanetary disk. So here, generally, in all these images, we're going to have ellipses. These are showing you the angular resolution. This is prior to ALMA, this is with ALMA. And you can really see it's night and day, the difference between these structures. Now, this is really reassuring because on one hand, we could see that the material was indeed centrally peaked as we would expect. They're sort of all contained with this blob, so we weren't going to be far off. But what we could see is that a lot of the dust was concentrated into these rings. So it wasn't a nice smooth distribution that we might have expected. We could see that that distribution was punctuated by gaps and rings. And if we're moving all that dust and material into those rings, perhaps this assumption that we're making of optically thin material doesn't really hold. Perhaps we're actually hiding a lot of material in these rings and we're just not seeing that coming from the emission. So this sort of poses a bit of a problem. How much mass is there in the dust? There are some ways that we can try and get a handle on this, and this is by looking at how the dust distributions vary with wavelength. So when we're looking at thermal emission from dust, the wavelength of the emission is typically around the size of the dust particles that are emitting. So when we look at something that is, say, 3 millimeter wavelength, so down here, we're looking at 3 millimeter size grains, essentially. Whereas if we're looking at these 870 micron wavelengths, we're looking at those much smaller grains that are around 870 microns. And if we look at how these dust features vary across those wavelengths, we can try and have a handle on actually what the dust distribution is within there, and we can try and circumvent this issue of optical depth and try and get a better handle on how much material is there. So this is doing a pretty good job, but obviously these are very expensive observations. If you have to spend the time to get these really wonderful observations where you've got really sharp rings, and do that over a number of wavelengths, that's going to be far too expensive to roll out to a whole population of disks. So it's only going to be really for a handful that we're able to do this. One interesting aspect that's coming out from these sort of analyses, though, that I'll touch upon later, is that many of these rings appear to have the same optical depth. So it looks like they have the same amount of a particular grain size. And this is across a number of different sources. This is particularly peculiar. And why would all the rings have exactly the same amount of mass in them? And that's something we'll talk about a bit later. When we look at the dust distribution, we can also see that these disks are slightly more complicated. They're not just these flat 2D objects. So these protoplanetary disks are essentially dust processing factories. We're taking the small submicron grains that are sort of populating the ISM, and we're building them into larger grains, which will eventually form planetesimals and planetary cores. When they're very small, these grains are going to couple exceptionally well with the gas, and they're going to go exactly where the gas is. And so when you look at these sort of submicron wavelengths, you can sort of see a very thick disk here. I don't know whether we can quite see it with the light, but you can see that you have this sort of faint shadow coming down at the bottom. That's because the disk is sort of like a can of tuna. It's quite squat, but it's definitely not a thin 2D shape. As the grains start to grow, they're going to decouple from the gas, just like snow or hail is going to no longer be lofted up into the air. It's going to fall down towards the ground. These larger millimeter-sized grains are going to fall down towards the midplane of the disk. And so when you look at the same disk at these longer wavelengths tracing the longer grains, you see a very flat disk, where all the grains have sedimented to the midplane. So you can already see by just looking at the dust, there must be gas there. There must be vertically extended gas as well, in order to loft these grains high up into the atmosphere. And ALMA has allowed us to start looking at this gas distribution as well. So prior to ALMA, these are sort of the observations that you would expect when you look at the gas coming from a protoplanetary disk. These show quite a complex pattern, and this is because we're looking at the rotation of the disk. What we record at the telescope is emission at a particular frequency. So each one of these panels is showing a slightly different frequency. And because the disk is rotating, one half of the disk is going to be rotating toward you, and so blue shifting emission, whereas one side is going to be rotating away, red shifting the emission. So that's why at the blue shifted frequencies, we see emission on one side of the disk, whereas on the red shifted side, emission is on the other side. At its central frequency, we see emission coming from the regions of the disk where we don't have any projected rotation. So this is what it looked like before ALMA, where you could sort of see that we have rotation, we could sort of see the broad radial extent of the emission. But it's really with ALMA where we're able to start to understand where that gas was. You could see far more clearly sort of the peaks of it. You can see these nice contours which are tracing the velocity structure of the gas. But what was perhaps most sort of important here is that we can start to see the vertical structure as well. Only were we able to measure how the intensity dropped off as a function of radius, you can see in some of these other channels that the emission splits into these two sort of arms on either side. That's because we're getting emission from the top side of the disk and from the bottom side of the disk. So with the same set of observations, we're not only understanding how gas is distributed radially, but we're also looking at how the gas is distributed vertically. And this is really important for understanding which of the hydrodynamical instabilities may be present in these disks. So now that we had access to this vertical component, we set about trying to measure this and quantify the vertical extent of these disks. So there was some early work by Christoph Punt that demonstrated how we could use these channel maps that I've just showed you to extract the emission height from the data. And we're able to make figures like this on this left-hand side. So this is the 12 CO emission coming from PDS 70, a very well-known protoplanetary disk. And these black contours I've drawn over it are showing you the emission surface that we're able to extract from the data. So you can see that it's sort of like a donut or toroidal, torus sort of shape. That's because this disk is flaring up in the inner regions and it drops back down in the outer because the emission is getting photo-dissociated. We also see that there's a great big cavity there. That's because there are at least two planets within here that are carving open this gap in the disk. So if there are planets there eating all the material, you can't expect it to have any vertical height. So that's why it only starts rising outside this cavity. Now that we're able to measure the emission height as a function of radius in these disks, we can use that same emission to sort of measure the gas temperature in them as well. And we're able to start making plots like I have on the right here, where each of these points is a measurement, as a sort of a radial distance from the star and a height above the midplane, and we're then using that to calculate the temperature at that location. Once we do this for a few molecules, which we know trace slightly different heights in the disk, we're able to start fitting empirical two-dimensional temperature structures to it. So that's what the background of this figure is trying to convey. This is the 2D temperature structures we fit to the data. And so we're now able to do this for a whole range of sources. And this is work that Maria Galloway-Sprietsma, a graduate student in the EXO-ALMA collaboration, is doing. She's applying this to all the 15 sources. And we're starting to get a sample of what the 2D temperature structures could look like in a protoplanetary disk. Really, for the last decade or so, we've been dominated by a very simple parametric form. But now we have the observations to go out and test this parametric form and understand how realistic that temperature structure actually is. The temperature structures you'll hear later is really important for understanding, again, which instabilities may be at play in planet formation. So now that we knew where the material was, we could sort of map it out radially and vertically. We still want to know how much of it was there. And the issue of mass is sort of a perennial problem in planet formation, understanding how much material is there. And this figure from Anna Miatello's Processes in Planet 7 review, I think really highlights the point. So for one disk, perhaps the most well-studied disk that we have, TW Hydra, we have all these different constraints on the mass. So you can see the disk mass down here, it spans 2 orders of magnitude. And depending on the particular molecule or whether you're looking at the dust compared to the gas, you can see a really large spread in the mass estimates. And while you might think, well, it's only maybe 1, maybe 2 orders of magnitude, it doesn't make that much of a difference. When it comes to the resulting planets that you'd get from population synthesis models, you see a huge difference between how effective this particular disk is at making planets and planets of a certain mass. So we really want to understand how we can measure the amount of materials in these disks. If we don't have that, then all the predictions that we make about population synthesis are completely wrong. So we do think there's a way that we can calibrate all of this, and this is thanks to sort of, again, this improvement in our ability to map the distribution of material in a protoplanetary disk. And that's to use gravity itself. Unlike emission, which can be optically thick, we can't see all the photons that come out of the disk. If we look at the gravitational potential of the disk and the impact that has on the rotation, that's not going to be blocked by being optically thick. And so this is a technique that everyone knows when we're looking at galactic rotation curves. The fact that if you measure the rotational velocity as a function of radius, you can get these really nice curves, and because they peak and then flatten off, you know there must be some contribution, radially extended contribution to the gravitational potential to give us that sort of profile. We can play exactly the same game for protoplanetary disks and try and look for subtle deviations in the rotation velocity from the expected Keplerian profile. This is something that we're trying to do, but it's incredibly challenging for a couple of reasons. Firstly, these disks are not that massive. They're not anywhere near the mass of a galaxy, and so the gravitational potential or the contribution from the disk relative to the star is minimal. So this is a very subtle perturbation we're trying to tease out. Secondly, we actually think the dominant term in the deviation from Keplerian rotation is going to be radial pressure gradients. These disks are in hydrostatic equilibrium, so that radial pressure gradient is supporting the gas against the gravitational potential of the star. Unless you have a good model for that temperature structure, and therefore the pressure structure, it's going to be very hard to tease out the additional component of the self-gravity. Nonetheless, I think we're there. In terms of the data, these are sort of demonstrating the precision with which we can measure those rotation curves. So these are the deviations in the V phi component that we measure relative to some smooth background, which we assume to be Keplerian. So you can see that firstly, we're seeing deviations on the order of 100 meters per second. So these are relatively large deviations for a disk, showing you that there is variations in there. We can do it for different molecules. So here, blue is 12 CO, green is 13 CO, and these are tracing at different heights in the disk as well. And you can see that for this particular source, they're both tracking very similar structures, which gives us confidence that the structures that we're seeing are real. And finally, the error bars on here, you can see are on the order of 10 meters per second. So we think we're able to measure the rotational velocity of the gas in these disks to a 10 meters per second precision, which is more than enough to be able to detect these subtle deviations. And so there's been a few works where people have tried to do this and applied it to a couple of disks. And we're building on that work and applying it to the sample of sources for the next farmer. And I think we can measure dynamical masses for about a third or maybe half of the disks that we have in our source. And so while this is not going to be applicable to all the disks, a lot of the smaller, like perhaps more common disks, are never going to have those signatures. This approach is at least going to allow us to calibrate the other ways that we try and measure disk masses. And this is going to really help understand how much material is in these systems. So I think this is a really big step forward.
Is this measuring mass of the disk, which is the gravitational potential of the disk mass, or is it actually measuring pressure?
So this is a combination of both. So this is just showing you the deviation from, say, a Keplerian model. And these variations come primarily from pressure variations in the disk. Yes, or gaps in the disk as well.
Right.
We can't show a nice Keplerian profile in the self-gravity where it goes super Keplerian in the outer disk, because we actually very rarely see super Keplerian motion.
So in that sense, it's not sensitive to the dynamical mass of the disk.
It is, because there's a difference in the radial dependence of the pressure profile compared to the self-gravity term, so you can differentiate between them. It's just you need to be very confident that you've got your pressure term correct, which is
I
a
was
trick.
just wondering, why do you think these measures for disk dynamical mass?
Because you can show you need to include the gravitational potential of the disk in order to explain the rotation profiles that we see.
Once you know the pressure gradient perfectly.
Yes, but because they have different forms, you need them. So this is still early work. I think we've convinced ourselves that we know what we're doing and we know what sort of observations that we need to push this further. But I'm pretty confident in the next couple of years we'll have really robust measures on the surface density profiles for a handful of disks, which is going to be really important. It's also not just the amount of material that's there that we want to understand, it's the composition. So particularly now that we're able to look at atmospheres, explanatory atmospheres, and see what's in there, we can go to bodies in our solar system, understand what's there. We want to understand what the material was like before it formed these planetary bodies. And so these are some results from the MAPS large program, where we looked at 5 different sources and just looked at what molecules were there. This is one particular source. I'm just showing you the sort of chemical variety that we're seeing there. All of these are different molecular lines, and you can see depending on the molecular line that we look at, you see very different morphologies. So some of them, like the carbon monoxide lines, just seem to span the entire disk. Others, like these simple hydrocarbons, show gaps and rings. Others, like slightly more complex organics, are only peaking up in the center. So this is an incredibly complex picture, and it's something that lots of people are still working on understanding, but it really shows there's a tremendous amount of chemical processing happening in these disks that are creating these sort of structures that we're seeing.
Question.
Yeah.
How optically are all these lines optically thin or suboptically thick?
It's an uncomfortable mix of both, and sometimes they can also vary. So these will definitely be optically thick. We think that some of them definitely are thick in the central regions and they drop off to be optically thin. So once you have multiple transitions, we can sort of understand which ones are thick or thin. But when you only have a single observation like this, it's hard to do that. One way that we really want to make...
Sorry,
Yeah.
Of course, these molecules all have different condensation temperatures as well.
Yeah.
So is there any self-existent story one can put together about the temperature profile just based on that?
Unfortunately not with these molecules, so a lot of that is going to really affect the inner regions of the disk. I'll talk a little bit later that we think we can see the condensation front of the CO, but everything else is much closer in that we can't really access. The way that we really want to make the connections with the atmospheres, though, is, I think, to look at the isotopes. So looking at where, say, 13 carbon, sort of 14 nitrogen, 15 nitrogen, these sort of things are, because that allows us to better trace that material through those chemical reactions and into the ultimate bodies. So this is a bit of a bright slide, but for one disk in particular, this TW hydrosource, we're able to start mapping out where the 13 carbon is and in which particular chemical reservoir. So on the x-axis here, I plotted the radius in the disk, so 0 AU out here, all the way up to 200 AU. And the y-axis is the ratio of 12 carbon to 13 carbon. So it's hard to see, but this is 60, this is 80, so this is around the ISM value here. You can see that depending on the molecule that we're looking at, so whether it's carbon monoxide or a carbon monoxide isotope log, or something that's, say, not got any oxygen in at all, you can have very different values in the amount of 13 carbon you have in there. And so this is telling us a story about how that material is processed in the disk and what sort of chemical reactions it's undergoing. And therefore we know whereabouts in the disk it will be when it's forming into planets. So we can make exactly the same measurements of these 12 carbon to 13 carbon in other bodies, and we can compare them. So we have chondrules, which are little sort of particles of the meteorites that we measure. We can measure the amount of 13 carbon in there, and you have a very depleted level of 13 carbon relative to 12 carbon. Whereas if you look in giant planet atmospheres, down at these two lines, you can see there's a lot more 13 carbon there than we have in interstellar medium. So this is still very early work, but I think it's going to provide a powerful way to try and connect the material that we're seeing in the protoplanetary disks with the material that we're measuring in planetary form, or at least in the meteorites. There's obviously going to be a lot of chemistry that connects these two, but having a handle on where these isotopes are moving through that chemical chain is going to really help understanding the sort of processing that the gas or the dust will undergo as it's forming exoplanets. So we haven't solved everything in terms of ingredients, but I think we've got a much better handle on where that material is, how much of that material is there, and what the composition is. We really now want to understand how we start combining that into making these planets. And this is a really tricky challenge. This is growing things over 40 orders of magnitude in mass in 1 million years. So that's a huge thing, huge challenge we've got to achieve in only a relatively short amount of time. And so there's a whole range of theories about how we can do this, how we can sort of bypass certain roadblocks in it. But essentially, they all boil down to the same thing. We need to concentrate a lot of the mass we see in a protoplanetary disk into a very small region. And once it's in that very concentrated form, essentially gravity will take over and we can build larger bodies relatively quickly. And so the main ideas here is the streaming instability, where if you start with very high concentrations of dust, it's going to very rapidly form these trains of material where they fall in behind one another to avoid the aerodynamic drag, and then they're going to clump into materials and then form these large planetesimals. So you can spend sort of multiple colloquia talking about how robust this formation mechanism is and the sort of conditions you need there. But for the rest of the talk, I just want to think about the fact, how can we get high concentrations of dust within the disk? We know there's dust everywhere. How do we really shrink it down into the space that we need? We've already seen from these observations, say from the D-sharp sample, that there are some mechanisms that are doing that. We're seeing that we have these rings of material and they're concentrating dust into them. And what's particularly interesting is that for a handful of these sources, we can see that these rings are spatially resolved, so it's no longer blurred, but we can actually see a measurable width of these components. And so this is some work that Kees Suleiman did, where he looked at these 5 sources and where he's plotted the radial brightness profile here in the blue lines. And these green and red Gaussians are showing you the rings that he argues are spatially resolved in the radial direction. So the dotted line is showing you the angular resolution of the data, and the solid lines are showing you the fits to the profile. And so he's able to show, under sort of several assumptions about how the dust is coupling to the gas, that if we have a finite width of the grains, or one that we can measure, then that sets some constraint on the amount of material within there. And what was surprising was this finding that all of these rings can be explained with the same amount of dust. So this is what I was saying before. It seems like all 5 of these sources and the rings within them, they all seem to share about the same amount of dust within them. So they all have an optical depth of around 3. And so this was really puzzling, why you would expect very different sources to have very similar properties within the rings. And Sebastian Stammler proposed that perhaps these are self-regulating. Essentially, we're concentrating material up to a particular threshold where another instability can be activated that is then going to grow that material into larger bodies, which we no longer see. And so long as we keep on replenishing that material, we're always going to see the same sort of amount of material in the rings, because anything, as soon as it reaches that threshold, we're going to form larger particles. Yeah.
Is this conclusion, is it successful with this argument about scattering limiting the optical depth argument? This is a little bit technical,
yeah.
I'm just curious.
So this does not take scattering into account. That could probably solve it.
That could affect it, okay.
Yeah. So none of the optical depth Kees determined did not take into account scattering here.
It's just the profile's quite limited, right?
Yeah, exactly. So there's at least some evidence that we're perhaps seeing this concentration of grains in a way that then can kickstart some self-regulating process. But obviously, we want to try and do a little better than just saying, well, we resolve the rings, perhaps there's a certain amount of material there. And the way that we want to get around that is by looking at the gas dynamics. We can use that to understand the pressure profile and the ability of these disks to trap material within the rings. So as I mentioned before, these disks are in radial hydrostatic equilibrium. And so any variation in your radial pressure profile is going to modulate the rotation speed of your gas. And so we were thinking about this earlier in the context of trying to find gaps in your pressure profile. So if you have a planet, it's going to become massive enough that it opens up a gap in your disk. And so you have a drop in your gas pressure profile around the orbital location of your planet. And that's then going to perturb the velocity structure, such that on the inner edge of the gap, you have a very strong negative pressure gradient, meaning you get very sub-Keplerian rotation. Whereas on the outer regions, you're going to have a positive gradient speeding up the gas. And so if we're trying to find this particular deviation in the velocity profile, we can be confident that we found the gap in the gas. Now, if we want to think about trapping of grains, rather than a minimum in the gas pressure, we instead want to see a maximum in the pressure. So all these grains should travel towards the regions of high gas pressure. So we can play exactly the same game, but just flip this upside down and expect to see a super Keplerian rotation on the inner edge and sub-Keplerian on the outer edge. So you should see a negative gradient in this delta V phi component. So we're able to look at those same disks that I was showing you before, where we had these spatially resolved rings, and also look at the gas velocity profile over those rings. And you can see that over those rings, we see indeed this negative slope in the relative rotation speed of the gas, indicating that we are indeed tracing the pressure profile across the rings, and we can confirm these are actually pressure maxima that are collecting the grains. So this was sort of the first demonstration that we could use this velocity technique to look at the underlying pressure profile, but we really needed better data to do something more quantitative. And this is something that we've managed to do in ExoArmor, where we've looked at the rotation profile for all 15 sources. And I think for about 75% of them, we've been able to show that every single continuum structure ring-like that we see here, we're able to see evidence of a pressure maximum. So we're seeing pressure traps all over the place, which is allowing us to concentrate all these grains. The one downside with this technique is it gives you the profile of the pressure, but it doesn't give you the normalization. You have no idea about any absolute scaling. Fortunately, this was solved by another graduate student, Tomohiro Yoshida, that noticed that when you look in the real weeds, sort of the noise of the data, you can see that these lines are not entirely Gaussian. So he was able to make a stacked spectrum taking the emission all the way around the ring, and that's what's showing up in this top panel here with these black lines. So you can see the level of noise down here is absolutely minuscule compared to the line profile. And when you zoom in right to the very wing area, you see that you have these wing components that can't be explained by the Gaussian profile, which is shown in light blue. And really, the profile can only be matched when we include pressure broadening here. This is allowing us to get a direct measurement of the absolute gas density of this ring as well. So in addition to getting the shape and the variations in the rotation speed, these very subtle line wings are giving us a way to normalize that profile and measure absolute deviations in the pressure. And so together, this is really going to allow us to understand how effective these rings are at trapping the material. Yes, we're still going to have to do a lot of work in understanding how much material is there, but now we know exactly what the gas is doing in order to concentrate it, and we can see how efficient the disk is at moving that material in there and perhaps bringing together those larger particles that we need to kickstart planet formation.
Which tracer is this?
This is 12CO. So you can see as well, it's not a pure Gaussian, it's sort of optically thick as well, which is why you have very steep sides and sort of a saturated core. So one way that we think we can sort of kickstart this process is perhaps using snow lines or condensation fronts. This has been sort of the idea is that as you move away from the star, the gas is going to get colder and colder. And at certain radii, it's going to become so cold that particular volatiles freeze out as ices onto the grains. So you can imagine exactly the same thing when you're coming down from a mountaintop at a very high altitude, it's going to be snowy. At some point, you drop to a location where it's warm enough that the snow no longer exists. That's exactly the same idea as what's happening in protoplanetary disks. And these ideas, or these snow lines, are thought to be where we can kickstart planet formation because they drive a very large density in icy grains. Essentially, you start with a lot of water vapor inside the water snow line, lots of water ice outside it. As the grains grow with ice on it, they flow inside towards the star, meaning that they're putting a lot more gas vapor here. As the gas vapor sort of increases in pressure and density here, it's going to slowly diffuse outwards and then refreeze again on the grains, meaning that you get a much larger population of icy grains just outside the snow line, where you can perhaps kickstart planet formation. This idea that snow lines as preferential places for planet formation have been invoked a couple of times to explain the architecture of our solar system. So these two planets both had models where we try and form planets, and they always had to start them off at, say, the water snow line or the carbon monoxide snow line in order to get the architecture that we see. So this is a really nice story, and I think it sort of holds together physically, but we haven't been able to detect these things in a disk to really study them in great detail. But we do think we're starting to see evidence for these things with the really high resolution data. So this is pretty hard to explain, but I'll try and go through it anyway. So this is a cross-section of a protoplanetary disk. We've got the radius here and the height above the midplane, and it's symmetric above the midplane. This black contour is showing you where carbon monoxide should be in the gas phase. So if it's above here, it's no longer shielded to the external radiation, which would photodissociate it. In the midplane here, it's too cold, and it's going to freeze out onto the grains. So you have this sort of pincer-like shape in where CO should be. When you then use this to look at what the emission would look like on the sky, you end up seeing this pincer-like shape in the emission profile here. So I don't know if you can see, but there's a sort of a single component here relating to the single component there. And then at some radius, it splits into these two arms, and that's where we get the CO snow line here, because you're no longer seeing emission from the midplane region here. So let's just try and highlight that point again. This yellow bit here, this is where the CO snow line should be at the midplane, because it no longer have emission there because it's all frozen out. So this is some work that my graduate student Jensen and another graduate student at Harvard are doing, where we're trying to use these really high resolution observations to understand whether we're actually able to see the carbon monoxide snow line directly in the disks. Because we're able to do that, we can then zoom in and spend a lot of time with ALMA to really zoom in and understand what the physical processes are here. Do we see it correlating with particular rings of dusty material? Are we seeing evidence of any sort of planet formation going on there? And can we calibrate the other techniques that people have proposed for finding snow lines, such as looking at other molecules that should anti-correlate with the molecule of interest? And this is going to really help us sort of expand this study of snow lines and their importance for planet formation out to a much broader sample. It's also not just radial trapping of grains that we need to do, of course. If you trap them radially, that's going to help. But if we can also azimuthally trap them and concentrate them, that's going to do a much better job of kickstarting planet formation as well. And there's now a number of sources that we know that host these azimuthal dust traps. So this is a compilation of 4 of the sources that we have within the ExoAlma project. This is some work done by my postdoc, Lisa Wolfer, where we're seeing evidence of these traps in the continuum. So there's certain regions of the disk that are definitely concentrating materials azimuthally. The hope is that if we look at the gas structure or the gas velocity structure, we can understand whether this is also being concentrated by large-scale instabilities or perhaps vortices. These are maps of the velocity residuals relative to Keplerian. So these are all the additional motions the gas is exhibiting on top of the Keplerian rotation. And you can see that it's really quite a mess. These are not as simple as orders as we had hoped or expected them to be. But we are seeing these large spiral arms coming out of where these vortices appear to be in the disk. And so we're working hard on trying to quantify the structures that we're seeing in the gas velocity structure. We're also having to run sort of quite expensive numerical simulations to understand what sort of perturbations we'd expect the vortices to excite. Yeah.
Are there any correlations between the presence of this counter-axis symmetry and the mass of the disk or the age of the disk?
Not really. It seems to be, just scattered around at the moment. I would caveat that with every disk that we're looking at in this detail is already on the upper end of being very massive and very big, and is probably not representative at all of the broader population. But even with that, we don't see a correlation within that. So this is some pretty tricky data to try and disentangle, and so there's lots of people working on trying to make sense of what we're actually seeing here, but we can pretty clearly see these things are highly dynamic and there's a lot of structure going on. And so this really begs the question is, what are the large-scale instabilities that are driving these perturbations? These are just 3 examples of the sorts of velocity structures that we're seeing with our ExoAlma sample. So say we've got a very large spiral arm here, say one that's got a very distinct sort of annular structure in there, and then one where we see this sort of correlated noise. These are much larger than the beam, so it's sort of correlated over some spatial scale, but it's clearly not completely random. And so we've been able to at least classify the structures that we're seeing into these 5 different types. going from quiescent, where we really don't see any evidence of dynamics, up to these sort of more structured ones, and then these perhaps more turbulent, messy systems. And this has been a really, I think, big finding, because 3 years ago, we wouldn't have thought that disks were quite so dynamic. Everything we assumed was that Keplerian motion dominated the dynamics of these systems. But now, for nearly every single system that we look at with detail, we're seeing this amazing sort of structure in the gas. There's really something going on in there. If it's not planets driving these features, there's a lot of hydrodynamical instabilities in there as well.
Do you have any idea what the typical Reynolds numbers are for these disks?
I can't remember off the top of my head, but I can give up to you. Yeah.
Large?
Yes.
Are this intensity or velocity?
These are velocity.
So why would they how can you subtract the Keplerian?
After we've subtracted, yeah. So these are, say, 10% of the Keplerian rotation. So these are still large, but when you make a rotation map, it would be dominated by the Keplerian rotation.
Yeah, so why would they look so weird?
Yeah, that's the
See
question.
it's a spiral or something like that?
So we don't see a spiral. We see some spiral arms in the intensity, and which we expect at the density, but they're slightly offset. So there's a lot that we don't really understand at the moment.
In intensity, there's no such thing.
There is in intensity
Oh,
as
sorry,
well.
intensity is also spiral.
And we also see it in the line width. So we can see the spirals that they have a broader line, which might suggest they're more turbulent along the spines of the spirals. So we are trying to understand what we're seeing here, and one way to do that is to compare this with numerical simulations of instabilities. And so we have 3 very common ones: vertical shear instability, magnetorotational instability, and then gravitational instability. And while they might look similar, there are distinct features within them. So this one is very annular. Everything is sort of in rings. Magnetorotational instability and the GI both offer very large spiral arms, but the GI gives much stronger sort of contrast between the spiral arms. So we'd have thought if we're dominated by one of these instabilities, we should be seeing that. Whereas everything that we look at with XRAMA so far doesn't seem to be quite so clear. That said, there is one disk that seems to display a pretty distinctive structure, and that's AB Auriga. So this is really lovely work by Jess Speedy, who's a graduate student. And she's looking at this system. So this is the line of sight velocity that we're able to extract. We have the red shifted side and the blue shifted side. And when you subtract Keplerian rotation from that, we're able to see these really wonderful spiral arms. And so this is a really excellent match to those gravitationally unstable models. And so we're fairly confident that this disk is indeed gravitationally unstable. It's very hard to get this number of spiral arms with that sort of contrast without invoking some level of gravitational instability. So there's still a long way to go in understanding what methods are actually there, but I think it's pretty clear now that we've convinced ourselves that all these disks are dynamic. They're showing evidence of lots of velocity structures, and we've got the resolution now to try and compare those velocity structures with our numerical simulations. We just need to make sure that perhaps we're not looking at one instability in isolation. It's probably going to be a mix of different instabilities, but we're definitely at the stage where we've got enough data now to try and challenge the numerical models. In the final few minutes, I just want to talk about the outcomes of planet formation, trying to understand how well we can constrain what the planet should be looking like once they've just formed. So there's only one real disk where we have really wonderful observations where we're sort of 100% confident that we're looking at planets, and that's in this PDS 70 system. And so what we're seeing here is this ring of outer material from the protoplanetary disk, where, say, terrestrial planets are forming. But we also see this single point source here. And this is just a zoom in of it. And this, we think, is the material that has settled around a recently formed planet, just the material that the moon system is going to form. And so ideally, this is what we want to do. Every single disk that I've showed you, we spend the time on ALMA to integrate until we're able to find the planets in all these gaps. The problem is these are exceptionally challenging observations to make. Simply in the amount of time, this one took us tens of hours just to make this detection. And so there's no way that we can really apply that to a whole sample. That's going to be really challenging to do. We need to think of different ways to understand where the planets may be within the disks. One way that we're thinking about is been trying to use other features of the dust that might point to where the planets are. And one of them is proto-trojans. So this is the idea that when you have a planet orbiting a star, it's going to have these Lagrange points where things can settle in because they're stable. And so as Jupiter has these L4 and L5 points, we're able to capture a lot of these asteroids in these regions that we call trojans. Now this should happen to any planet that orbits a star, and we actually think we have reasonable observations of these sort of clumps in other systems. So this is work that was led by Feng Long, where in these two disks, when you subtract away a mean background, you're able to see these overdensities that are exactly 120 degrees apart from one another, the same radius. And so if you assume that these are L4 and L5, we know exactly where the planet must be lying in order to make that stable. So because we have a good idea of where to look, we're able to point our telescope to this particular location and see if we see anything. So we're currently conducting a survey with gravity, zooming in at this very sort of precise location to see whether we see evidence of any planets. This is pretty challenging because although we can sort of generate quite large differences in the amount of millimeter dust that we trap in these Lagrange points, the planet masses that we need are very, very low. These are sort of Earth mass, Neptune mass planets. So this is still going to be an exceptionally challenging observation to make if we're to tease anything out. The other approach that we can use is to try and look at the gas structures and see if there's any evidence of planet disk interactions that we can use to sort of convince us that we're looking at a planet. And so TW Hydra again is a nice example where we see these spiral arms emanating from the same location that we see a gap in the dust emission. So this right panel is showing you the scattered light from sphere, and on the left we're seeing the gas velocity structure where you do see these spiral arms coming out from exactly the gap location. So we've got fairly good chances that there should be a planet around there. And so we're using things like JWST to follow up these observations and see whether there's evidence of any planet or sort of localized accretion heating that would portray something that would be carving open this gap. Sometimes the features aren't as sort of obvious as we'd like, so these large spiral arms. In some cases, you have to look for very subtle perturbations in the velocity structure. And one way that we do this is by looking for what we call kinks in the emission morphology in a certain channel map. So these were the channel maps I showed you before that are bending round, and each of them should be tracing a very particular velocity where the projected Doppler shift means that all the emission comes from the same frequency. And so in a smooth disk, these should also be smooth isovelocity contours. But at some disks, you can see that they have this distinct sort of kink-like feature. And so in the central panel, we're zooming in on that kink-like feature, but you can see that the crests do make this sort of break. And we think that this is due to a planet being there in the spiral arms from the planet, perturbing the velocity structure, which gives rise to this break. When we look at the other side of the disk, we see a very smooth region. So we know that the perturbation has to be localized within this region of the disk. And so using this approach, we can try and find the presence of planets in a whole number of sources based on how they're perturbing the local velocity structure. So we've done that with our exo-armor sample. There's a whole load of these features that we're seeing, but these are probably the four most prominent ones that we have so far. And these little X's are showing you where we should be expecting those planets. So these are showing the total intensity of the 12CO emission. These bottom panels are showing the channel maps where we've overlaid sort of subtle kink-like features that we expect to see. And so we've submitted some time for JWST. We've made predictions about what we'd expect to see in the mid-infrared if these are real planets. And we're just waiting for the data to come down and for us to be able to see whether we're seeing anything.
Those are
These are predictions, yes. This is what we put in the proposal. This is
what's the red spot? What's the red spot?
The red spot is the planet.
On the predicted red spot.
Yeah, so the blue is negative, the red is positive, and these are all the planets that we should expect to see with other significance if we assume there's no disk material there.
When they didn't know.
So we've got two of the sources already, and we're going to get another two. Just trying to make sense of the calibration is really, really tricky. So I think we've got a good idea then of what the planets should look like. It's a very tricky thing to do, but we've got multiple different avenues that we can use to try and understand what planets are being formed by the planet formation processes. So to just talk about what I've sort of discussed very quickly is that in terms of the ingredients, we're able to now map the radial and vertical distribution of the gas and dust in these systems. We have ways or ideas on how we can actually constrain the amount of material there is there, and we have sort of several techniques that we know how to improve to do a better job in the coming years. And we're able to also catalog the chemical diversity of the planet-forming material, so we can really compare that to what we're seeing in atmospheres and in, say, planetary bodies. We have a really good idea of the dynamics within these disks, and so we can use them to understand where planet formation may be happening. We can understand which of these processes are concentrating material and those which may be disrupting it. And by comparing with numerical simulations, we can have a good idea about which of these mechanisms are really the dominant or important ones for planet formation, and the other ones which are maybe less so. And in terms of the outcome, there are several approaches that we're using to try and detect these young planets. We have a few examples of them, so we know that they must be forming planets in one way or another. And there's several different groups that are spending a lot of time trying to perfect these techniques, so we know exactly what we should be looking for at the end of the planet formation process. So with that, I'd like to thank you for your attention. I'd be happy to take any other questions if you have them.
I'm still a little confused about how you distinguish between the degeneracy from the pressure gradient and a change in the Keplerian velocity from pressure gradient versus from solar gravity. Can you talk a little more about that?
Yeah, so if you were to, I should put this figure in because this has come up a couple of times. If you plot the two-dimensional perturbation on the velocity that you'd expect from those various components, they have very distinct spatial distributions because of the temperature structure you assume and then the density structure. So because they have a particular shape in this RZ plane, you can only use one you can't just use one and scale it up to reproduce your D5 profile. You really need a combination of them in order to correct the correct shape of the perturbation.
So does this sort of amount to assumptions about an equation of state that you're...
No, it really comes down to your assumption about what the 2D temperature structure looks like and the way that the emission profile through the disk varies. So if you think about, if I go back to this CO here, because we can measure this sort of shape very well in our data, we need to know what the velocity perturbation is at this sort of set height. It's not just doing it across the midplane, it has to be as a function of R and Z, the disk. And because the way the pressure profile perturbs the velocity structure is different from how the gravitational potential of the disk, at different heights, they vary independently as a function of height, you can break that degeneracy between them. So
does that assume some vertical dependence of, for instance, the density profile? Or?
Yeah, so we have to assume it's hydrostatic equilibrium in the vertical direction as well, and the temperature profile. And so with enough data, we can get an empirical temperature structure, which we've shown doesn't bias it enough. But you need to be able to measure this emission height, so we can't do it for face-on disks. If you don't have any information about how the height varies as a function of radius, we can't break the degeneracy. You really need that. And so there's a really nice paper by Catherine Rosenfeld, 2012, I think, where she has panels of how these different processes affect it. And you can really see that there's a very different functional form for them.
How much is WSD improving our knowledge of the structure of the enterprise?
So JWST is doing a fantastic job at cataloging what is there, but we don't have any spatial resolution. So this is the real issue, that we have essentially one pixel for that region, and everything that we do in terms of trying to understand the structure is model dependent. So if you have a disk model structure, you can leverage that to try and tease more out of the data, but it's very dependent on what that is. So this is going to be the NFUAU. So you really need to be in that close to get the gas temperatures hot enough such that the gas is sort of emitting at these mid-infrared and near-infrared wavelengths. You only achieve that near FUAU.
And just more broadly, I mean, how constrained are the radio surface density distributions?
Very poorly at the moment. So because we don't really, the only tracer that we know that really spans the full extent of the disk is 12 CO. And because that's optically thick, we don't really have a good idea about that. So with the dynamical mass I was talking about, we think we can also do the slope of the surface density profile. So I think there's some room there. We've got a bit of work to do and we need slightly better observations, but I'm fairly confident that, as I say, in the next few years, we will get at least the slope for a handful of disks as well. But it doesn't look like we're too far off from our general assumptions of what they should look like, which is reassuring.
Well, wait a minute, what, I mean, there's like a huge difference between mass or surface density going as radius to -1.
Yeah, that's right.
How the mass is distributed within the disk.
So that's right. I think I'm always saying this from a very biased sort of outer disk perspective, where it doesn't make too much difference to the mass we're looking at beyond 10 AU. But you're right, for the inner disk, that slope is going to make a huge difference. And really, that's actually the region where we don't have a lot of resolving power. It's still going to be sort of 10 AU outwards, so we can measure this for it.
Any final questions?
We can go upstairs, we got coffee. Coffee.